So today we're going to talk about earthquakes in Latin America, following with the module where we talk about energy, natural hazards, and this is one of the first of these natural hazards. So earthquakes in Latin America. First, we're going to start talking about generalities of earthquakes, and then we're going to talk about a few of the main earthquakes during Latin American history. So earthquake is the term that we use to describe all the effects that happens during one of these seismic events. The slipping default, that is something we normally don't see, the shaking of the ground, and the radiation of the seismic energy normally radiating from one particular point. And that's earthquake for us. Earthquake hazard is associated with the disruption of normal activities, including fatalities, including breaking up of different communication ways, energy, and sometimes all the related effects of tsunami. In particular, we're going to talk about tsunami as one of the major effects of earthquakes in this disaster situation. We're going to define a particular region where earthquakes are very, very frequent. It's what we normally call the ring of fire. The ring of fire is because volcanoes, as you can imagine, but also we have associated the ring of fire to normal tectonic activity, not abnormal actually, more than normal tectonic activity, and that is also a place where we see earthquakes. So in particular, what we see here, the ring of fire all around Latin America, South America, Central America, going through North America, the Aleutians, the Kirill Trench, Isuanin Trench, Mariana Trench, and then goes ending into the Tonga Trench and the associated islands of New Zealand. So the ring of fire, that's the reason why we call it. This particular map, we have marked in here all the area where we have all these tectonic activities and places where we have extreme subduction, producing really deep oceanic trenches. In particular, the deepest one happens to be the Mariana Trench, followed by the Japan, Kirill Trench, Tonga Trench, and then Peru-Chile Trench is also important. In the Atlantic side, we have only one, the Puerto Rico Trench. It's rather important too, isolated, and it's not really forming part specifically for this ring of fire. As we know, this is something already been explained by Dr. Stern in previous talks, but we do have three different possibilities of a plate, rigid plate, to move against each other. Either they can pass against each other with a transforming fault, they can diverge from each other into a line that normally is what we call the ridge, or they can encounter each other, one of them goes under and the other ones prevail. So this is normally what we see. And in general, we're going to see here this number 3 is the one where we have the most important effect for earthquakes, followed by also number 1 here, of transforming faults in importance. Number 2 happens to be also seismic, but since the temperature in this area happens to be higher, so the behavior of the rocks, or the plate, I should say, is more plastic than solid. So instead of deforming and slipping along the fault plane, it tends to deform and flow in a way that is not really conducive to produce strong earthquakes. Anyway, so if we plot all the earthquakes from 1975 to not really to the present, but let's just say the present, about 10 years ago. So we see here a colorful map. In particular, the colors are assigned depending on how deep the focus of the earthquake happens. So from 0 to 33 kilometers down is in this color. Then we have yellow from 33 to 70, and the deepest earthquakes are in red here. So we see here there is a three-dimensional component to the location of the focus for these earthquakes. And all of them tend to be in this ring of fire we see here, following in this area here. Interestingly enough, we have a few places here, here, and here where earthquakes are less frequent. You're going to see why. This is a better map. It's actually coming all the way to, it's fairly recent. But here we plot all the records from more than 7th magnitude. The 7th magnitude is a very large earthquake. And in general, we see it's a good marking of the boundaries of the active margins, particularly subduction margins. Divergent margins, like we see here, do have a few, but most of the earthquakes are lower than 7th. Same here. Most of the Atlantic, which is a divergent margin, don't really have many, except in a few places where we do have a few transforming faults. That's probably the reason we have earthquakes of 7 or larger. Let's see. Most of the earthquakes are concentrated, larger earthquakes are concentrated in subduction zones or transforming zones, like we see here in Turkey. Very large situation with two sets of faults moving against each other in a transforming fault with very strong seismic events. So, in general, when we try to explain what happened in a subduction zone, we'll see something like this. An area that we call the subducting area that goes under the other plate, eventually reaching sun melting in a particular point far away from the trench, which is right here. And then it's one area where we have the maximum event recordings. It's called the seismogenic zone. It happens in here where we have the maximum friction in between the plates. And later, we do have friction in here, but less because the temperature is increasingly larger as we go in this direction. So that's the reason we have a concentration of a majority of a large earthquake occurrence in that zone, the seismogenic zone. Seismogenic zone, if we take that zone alone and put it into a cross-section, we see something like this. All these are representing focus of different earthquakes and marking quite well where the subduction plate goes under. So it happens between about 18 to 0 kilometers. In fact, in 0 is quite impossible. In general, it happens about 10 kilometers and 18 kilometers or so. In this particular configuration, it happens in the trench. The subduction happens to be more steep. You're going to see that is translated in a shorter seismogenic zone. So all that is important. Now, the magnitude of the earthquake in general is a number that is trying to represent the energy involved in this event. In general, the moment magnitude goes from we have here 4.2, 5.2, and 6.2 here. You see the energy is increased by tenfold every number that we go. So it's a scale that goes increasing not in a linear way, but in an order of magnitude every time we increase one number. So the difference between one earthquake of 6 to an earthquake of 5 is rather dramatic, particularly with the measure of the oscillation in the energy. So the magnitude is measured by the motion in a seismograph, which is produced by a seismogram. The moment magnitude is based in this measurement here is the seismic moment, and it's very well applied to all different kinds of earthquakes. So this is what we use nowadays to explain and measure earthquakes. The seismic moment is a measure of the size of the earthquake based in the area of the fault, the amount of slip, and the force that is required to overcome the friction, making the faulting in the place. A typical seismograph is representing different waves. The first wave to arrive into any place from one particular event is called the primary wave. That's why it's called the P wave. And the second one coming after is the secondary wave, or S wave. The difference between the P and the S arrivals is representing how far away is the epicenter of the earthquake. And then later we have another set of waves, which we won't really talk much about it. It's called the S, surface wave, actually, no S, but surface wave, no secondary waves. So what we have here is an earthquake that happens in 2001 in Tacoma, Washington State. And we see it was a magnitude of 6.9, and the arrival time between P and S is defining how far away it is. This is normally measured in time, as you can tell, the time of arrival of the P and the time of the arrival of the S wave, and later the surface waves are also important because they exacerbate the damage, but it's not really something that is giving us much more information about anything else. Now, in an earthquake, we can actually distinguish two different stages, what cycles you want. What we see first is the interseismic period. This is long. It may go from the 10 to several hundred years. And it happens to be the moment where this is charging. It's charging like a spring by increasing the compression and locking that energy into the friction produced by the rocks. So that thing happens, and when that happens, we see these two effects: a subsidence here and an uplift here. That is part of the elastic response to the effort of this plate against the other plate. This is the South American plate, and this is the Nazca plate. In this particular place, South American plate and the Nazca plate is what happened in Chile during 1959. We have a very strong earthquake, one of the strongest earthquakes ever recorded. So we do have deformation. This deformation, right now, it can be measured. You know, we do have the tools to do it. And probably in the 1960s, didn't have it, but right now we can measure the subsidence. It's in the order of 1 to 5 millimeters per year. And the uplift, got no numbers in here, but you know. This is something that happens over a long period of time. And the second stage, much more brief, may last for a few minutes, seconds even so, and is the rupture. So we see here the friction is being avoided, the rocks break, and the release of energy happens all at once. But not really all at once, but in a few seconds. So what we see now, instead of a subsidence that we used to have here, now the opposite. Bounce up quickly. And what used to be uplifting now goes down. So it's like the whole thing that was being loaded in this way and this way now goes the opposite. During this event, we do have a sudden release of energy. And that energy is also producing very large displacement of coastal areas and water in that fact. And that displacement of large masses of water is the perfect recipe to produce tsunami. Tsunami is a plural per se. It doesn't really have to say tsunamis with an S. So anyway, once this happens, the whole thing may start again and keep going for another 100 years or so. This is the best model to explain what happens in the 1959-60 Chilean earthquake. More or less, this is what happened in all the earthquakes we see. Here is the same thing, actually, in a paper by Gutcher and Peacock in 2003, exactly the same thing. A kilometer from the trench right here, 0, all the way to 200, 0, 200, and the uplift and subsidence. Now, three things we should talk about when we talk about an earthquake. The epicenter is right on the vertical where the whole thing happens, which is the hypocenter or focus. Either one is actually a synonym for each other. So it may happen quite deep, but the place where the maximum damage happens is right on top of the vertical. Yeah. So, and that's the place we would call epicenter. Yeah. This is an interesting graphic for an earthquake that happens in Landers in Los Angeles in the 1970s. What we see is a magnitude 7.3 earthquake, and the interesting thing is a fault. And what we see here, this is actually a summary of what happened during that fault in this animation. What we see here is different deformation along the fault. As you see, it's not really uniform. In places where the deformation is larger, and in places where the deformation is smaller. And in the same way, it happens with the energy being released. So the more deformation, the more energy is released. So what we see here is in meters, how much displacement happens in those different places. So we see here in this particular yellow here is about 6 meters or so. So this place is a place where we have a high displacement. Same here, probably the largest. And then here, very little. So we see the formation. It happened to be not really equal all over the place. So what we're going to see what happened in time, because this is not just something that happened at once in a very large fault. This is far away. Let me see if I can get, yeah, right here. So in total, this is including 100 kilometers from here to here, 60 miles. And we're going to see the origin is this point here. And then the propagation of this effect happened to be breaking the locking of this fault along the area going in this direction in different ways. So you're going to start doing it. It happens to be a sequence. I won't be able to stop, but it's to an interval of 1 second each. So it's the first one. 2 seconds later, 8, 10, 12, 18, 20, and that's it. In 24 seconds, we move from here 100 kilometers in the direction of the fault. So you see the propagation of the earthquake, it happens not because it's just one earthquake here, but that earthquake happens to be triggering other events along the fault. which were in a different stage of energy load. And as such, we may have stronger places in the area that where the displacement was larger, and obviously the earthquake was also larger. So in total, this is the summary. The rupture on the fault is marked by this very interesting map with colors indicating the magnitude of the displacement. Displacement or slip, same thing, right? So this is important because it's representing that earthquakes are not really something that happens in one particular small point and then propagate around. No, it happens to be separated for a distance, and depending on where we are, the energy may be adding up as we go. So what we see here is a direct correlation between the faults and earthquakes. So the larger the faults, the larger the earthquakes. And we see here the extension of the fault in, from 1 to 1,000 kilometers, and the magnitude of the earthquakes is showing a very direct correlation. So we see to have earthquakes close to 8, we have to have a very large system of faults that accumulate energy. So, Latin American history, more or less is summarized here since 1900. The 10 larger earthquakes in South America, Central America 5, 1 in Mexico, and 1 in the Caribbean. Mexico should be put together with North America, obviously. Let's see here. According to the damage, we can quantify the damage using the number of fatalities. We see here 2010, in January 12, we have 1 in Haiti, magnitude 7. That's the largest, I should say, the deadliest earthquake ever in Latin America so far. Now, if we look into the opposite way, see 9.5 magnitude, this is the largest earthquake ever recorded. It had only 5,000 deaths. It happens in 1960 in Chile, and it happened to be affecting areas where the population was not really very high. The opposite happens in Haiti, where the population was quite large and also concentrated in a few places. But see here, we go from 7, the deadliest one, to the largest one ever recorded anywhere in the world, the one in Chile. You go into 5.5. It happened to be quite small. If we think about this scale, that is 1 order of magnitude every time we go one number. 5.5 should be very small, but instead here we do see more than 1,000 fatalities. 5.6 in Nicaragua, 2,400 fatalities. So sometimes the correlation of the magnitude and the casualty numbers are not straightforward, as you can obviously see. Now, why we do have so many Latin American earthquakes and why they are so strong? But in general, this is what we see. The typical Chilean convergent margin is a subduction where we do have a young lithosphere. Being young means this thing is not really easy to sink, tend to be up. And in that respect, it's producing much more friction here, and hence more and stronger earthquakes. Now, the opposite happens in the West Pacific. We see here, this is the Mariana Trench in here, deeper trenches, and the oceanic crust that is going under there is the oldest oceanic crust anywhere. It happened to be quite close to lower Jurassic in age, and it's sinking quickly, very quickly. It's producing earthquakes, obviously. We do have earthquakes. There's a very good record of this, but the earthquakes are very weak compared with the others. So we do see a quick deepening of the subduction zone. But the subduction is young, hot, and buoyant lithosphere is the reason why we do have much larger earthquakes in Latin American area. And in that respect, we see here in this map quite well the age of the oceanic crust. You see here younger, 0 to older, 180. There is not really any other older crust in the ocean. And so we do have here, this is the Mariana Trench, very old crust, and this is the Chilean area where we have the Nazca Plate. And this is quite young, that's why it's much more buoyant. So we do have also some anomalies, particularly easy to observe in South America, areas where we see something called flat slab regions. Flat slab as opposite to normal slab here. A normal slab goes down, we see a continuous increase in temperature, more or less in this area here where we start to having melts, differential melts, they're going into producing the volcanic arc. So the seismogenic zone here, and then soon enough the seismic activity is less. Now, there are places where we see subduction like this, and then a level of the slab, and going more or less in a flat way. And this is important because this area here, it doesn't really reach the melting point. It doesn't produce volcanoes, but it does increase the friction area. So this is the worst situation for large earthquake. So earthquakes are prone to be having this area, and but this area here got no volcanoes, no volcanic activity. There's no active volcanism. And here we do see volcanism. So interestingly enough, we see here these two configurations are producing different settings where we're going to see majority large earthquakes, no volcanoes, and then volcanoes and a few earthquakes with less energy. We put that in a map. You can actually see it in here. Flat slab segments here, 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 and this area here. We got another one here in the north part of Washington, Oregon state, and a few more here. But those areas are very, very strongly seismic, with potential to become extra strong seismic events. It's affecting only 10% of the global subduction zone, but it's still important enough. Here we have a detail from the paper from Gutcher in 2000. You see the flat slab area here, another one here, and another one here. And right here we do see these red cones as areas we do have volcanoes. And in between, no volcano here and no volcano here. Again, as we go into the bending of the Andes, in here we do see volcanoes again. So volcanic areas here, volcanic areas in here, and volcanic areas in here. Those are the places where we don't have flat slab. And opposite to that, we do have these extremely seismogenic zones where we do have only earthquakes, more than volcanoes. This is a rather unusual way to present your a map. Normally maps should be oriented towards the north, as we see here, right? Well, this is presenting South America as we see it looking from our perspective. So what we see here is the Nazca plate here going under into the subduction, and here where we have the flat area. So all this area between the Nazca ridge and the Carnegie ridge is an area all flat slab regime. And then obviously they go down and continue towards the central area. So again, this is actually redundant, but what we see here is a greater release of seismic energy with flat slab regimes. And obviously when we have a steep lava segments, we do have a preponderant melting of the upper part of the slab, where we do have volcanoes, and obviously we do have some earthquakes. But here, these areas representing places where we have a maximum of the seismic energy. And here is almost nothing. Anyway, so flat slab, earthquakes, steep slab, volcanoes. And we see here, FS and FS separated by volcanoes, volcanoes, and volcanoes. So if you're going to see volcanoes, you got to go to South Peru, but not to the central North Peru. There's no volcanoes in there, no active volcanoes at least. Same thing here. You're going to go and see the boundary between Chile and Argentina. Here, this is a place where there's no volcano really, but the farther south is full of conical, beautiful volcanoes. Now you're going to keep track of the earthquakes. Are very interesting tools. By all means, I put these links in here for you to see it. Worldwide, we do have this link in here. This is Central America and Caribbean here, and South America, this one in here. All these are keep up to date by frequent logging of recent earthquakes. Even today, you can see the earthquakes of the day using these important tools. Most of them are administered by the USGS, which is a wonderful organization. So, all in all, in the whole planet, we do see marking here the 10 most powerful earthquakes since 1900s. So, as we mentioned before, the 1960 Chilean earthquake. Then we do have another one in 1964 in Alaska. And then we have in 2011 the earthquake in Japan that actually was responsible for one of the most powerful tsunami observed in recent times. And another one in here, this happens in the middle of the ocean in Sumatra, and it happens to be producing a very large earthquake underwater that was responsible for one of the most deadly tsunami ever observed all around the area where it happens. And then we have the Chile earthquake we mentioned. Then we have another one in Chile with 8.8, and another one in Colombia in 8.8 in 1906. So we may mention a few of these as a case of a study. The Chile earthquake in 1960, this is the most important earthquake ever. It happened to start in May 2060, and there is a series of earthquakes changing hypocenter of focus as we go. All in all, affecting all these fault close to 1,000 miles or so in length. So the whole thing is part of the event. Very much it probably happens like we saw in that model from the landers fault, where one earthquake starts and then start triggering other earthquakes along. The damage wasn't really much because it happened to be in the southern part of Chile, an area where is not really much population. It was a tsunami produced by the earthquake. It was triggering warnings in Hawaii, and in fact, it was observed a tsunami coming from that event in the area. Some of the historical photos from the area, see the construction in this part of Chile is mostly made out of wood, so actually it's a good thing because people can get out of these destroyed buildings without too much harm. This is in Valdivia, one of the largest cities in that area. Most of this happened because the soil that was saturated with water under the effect of an earthquake start to lose water and start losing at the same time the capacity of supporting weight. So as you see here, most of the things sunk into the soil. It happens in many different places. There is a very interesting paper by the USGS, part of a circular 1187. It was published in 1999, well, you know, several years after the event. And it's talking here about those events that we talk about, the loading time up to this point, and then the triggering of the earthquake happens in these two things probably happens in a few minutes. So the release of the uplifting and the increase in the area where it was subsidence, that actually trigger energy, and that energy is moving water in the whole length of the fault, producing a very large tsunami. That's the reason tsunamis start to move right away. Isla Moca is a place close to the area it was affected by the earthquake and the following tsunami. Here we see what happened. This is Quilihue in Chile, quite close to Isla Moca. And see, this is before, there's a river here, and then after the tsunami went over, see all the buildings are essentially gone. They were talking about 13 feet of the tsunami, but you know, the tsunami is really difficult to stop at all. In Chile, one of the valleys that go into the mountain and see the wave was about 10 meters, you know, about 33 feet. All this was essentially washed over by the event. You know, this is what happened in Hilo, in Hawaii. This earthquake in Chile, way far south, affected this place. Hilo happened to be right here, and the tsunami came from the north, in fact. Even so, it happened that tsunamis are very long waves that are actually affected by the depth of the bottom and the shape of the bottom of the ocean, very deep. So it's affecting the way those tsunami arrive by refracting and diffracting the wave in a very interesting way sometimes. We see here Hilo pointing north, as we see here. It was affected by the wave coming and flooding all this area here. Essentially, all the lower part of the city was flooded by seawater. Not just once. You see here, this is what it was recorded. The first wave came over here just after midnight, and then at 1 a.m. the following day, we're still having some other wave coming. So it's not just one. Japan also got a record from this earthquake in Chile, the tsunami produced in Chile. So here we have a few places in Japan that recorded this tsunami. They count in Japan 100 deaths, 85 missing, and several thousand homes being destroyed. So Japan is one of the countries that is better prepared for earthquakes and tsunamis, and even so they do suffer the consequences of any of these events. Now, if we try to go a little deeper in time, 1500 or so, it's quite difficult. In general, we try to reconstruct this by historical documents, records, and such. And in general, we may talk about the number of fatalities per earthquake. And here we try to represent this by size of the circle and the particular color. And see, we see here Asia being devastated by earthquakes many times, and also the records from Asia are much more deeper in time than any other place. So those are the major earthquakes we have recorded. Obviously, we don't really have a way to measure the magnitude of these earthquakes, so numbers don't really make much sense, but you know, number of fatalities does. We do have here 500,000 to what we have here. Yeah, it's close to 1 million or so, but it's very difficult to establish all that. Before 1900 in Latin America, we have several of them, particularly all coming after the records from the conquistadors and later from historical records from different countries. So we see here one of the deadliest one happens in Ecuador and Colombia in 1868. Magnitude 7.7. This is an estimation, all right? It's not really a certainty about. It can actually, scientists go there and measure the effects in different areas, still there, and measuring the deformation in the rock can actually establish some correlation with the magnitude. See, one very large one happens in Peru in 1746. You got about 18,000 fatalities. For that time, 18,000 was incredibly large. So, important history of earthquakes in Latin America. So we're going to talk about the Peru earthquake. It was a massive earthquake in Lima in 1746 and 10:30 in the night. The area was heavily affected. And the problem here was essentially that all the houses were so close together that the whole thing becomes a continuous accumulation of rowley that couldn't be removed easily. After that, we're going to see later, they opened the streets in a much wider fashion in order to avoid this kind of situation. But in this earthquake, the estimation is as much as 6,000 fatalities during this infamous night. And they did also have a tsunami in the Callao. Callao happens to be the port city of Lima. Almost everyone died there, so 10,000 inhabitants and all the buildings destroyed, so harsh. And this is actually a textual correlation or chronically of what happened here. Somebody that was somewhat experienced to what happened with earthquakes, they said so far that we never saw something like that, in other words. So, you know, very, very deadly earthquake. So Lima, right here, it's a little higher, Lima out of the sea, and the port city is not far, called Callao. So that's the area where the major effect happens. So where's Lima? Well, Lima is right here now. This area, and Callao is over here. Well, we know Lima was founded by Pizarro. It's the capital and the political center of Peru. Population 6.5 million, inhabitants. So today is one of the largest places where population concentrate in Peru. Very important place for all. So, as we mentioned, after the earthquake, people start to realize better buildings get to be done for this purpose. So, streets were made larger, wider, facades were discouraged. It used to be an important architectural idea in those times, that they were actually making a very large frontal part of the building in order to, make it more important. But that thing is, you can imagine during an earthquake, that thing is a very important problem for everybody that happened to be under that area. All right. The walls that used to be around the city were no longer kept in the same way, so cities start growing out of it. We have another earthquake much more recently in 2001 with a magnitude of 8.4, which is quite important. So epicenter is right here. And obviously, the epicenter happens to radiate out of it in different ranks of similar energy. So this earthquake wasn't really important because it's very far away. We do have damage here and there, but this is an area far away from areas heavy population. We see a record of 102 fatalities, damage in places, but not really very important ones. So it's all depending on where it happens, obviously. Yeah. This is a similar, is the area too. We see here, this is a view from the north. Here is the north, toward the south. And this is the coastal area. So this is the Pacific Ocean. Why we see it white is not really because the water is white, it's because the fog. This current coming in this direction, it happens to produce also very thick banks of fog, in the same situation happens in California today. Water cold, the air is warmer and dry, so banks of fogs are quite important. So, very lonely place, far away from many places where population happens. These creeks, these canyons going into the Pacific are really deep ones. Very, very arid region. And see here, Rio Kona is this one here. So we're gonna see it in another satellite imaging here. Rio Kona is this one. Now is showing the coast. The Pacific Ocean is quite well. And this is the area where we have some cultivation and a small city here. So the quake epicenter is here, and the effect happens to be affecting to all this area here, producing a tsunami that we're going to see right now here. This is the area where tsunami was recorded. So destruction happens, but nowadays people knowing where they are and feeling an earthquake, they can actually establish points of evacuation. And in this situation, the evacuation is not really too difficult because they happen to be quite close to the mountains in here. So moving away a few blocks may actually be the easiest way out of danger. So this is the last example we're going to talk about. There are many, and actually if you go to the USGS, we can actually observe many of these events, happenings, very much every time. Even now, right now, you go to the USGS, recording the last earthquakes from the day. You can actually see one a few minutes ago, and I know precisely where it's coming. Anyway, all right. Next time we're gonna keep going with this chapter about energy and natural hazards, and we're gonna talk about volcanoes. It's a quite fascinating subject too. Volcanoes do have to do also with this, since we mentioned flat slab regime, no volcanoes, step slab regime volcanoes are much more frequent. All right, well, thank you very much. That's it.